Data poisoning is a targeted attack that alters or injects malicious samples into the training dataset, compromising a model's integrity and leading to persistent vulnerabilities such as systematic misclassifications or hidden backdoors that can be triggered later. This manipulation occurs during the training phase, allowing the attacker to influence the model's behavior over time. In contrast, model inversion attacks exploit a deployed model by sending carefully crafted queries to infer and reconstruct confidential data from its training set, potentially revealing sensitive personal or proprietary information. Both attack types target different stages of the machine learning pipeline, but share the characteristic of exploiting trust in the model's data and design. If left undetected, they can cause severe breaches of privacy, data integrity, and operational security, highlighting the urgent need for continuous monitoring, validation, and robust defense mechanisms across all AI lifecycle stages. Data poisoning is a malicious technique that alters or injects corrupted samples into a model's training dataset, undermining its integrity and embedding persistent vulnerabilities. This can result in systematic misclassifications or the creation of hidden backdoors that activate under specific conditions. Model inversion, on the other hand, targets deployed models by sending crafted queries to infer and reconstruct sensitive information from the training data, risking the exposure of intellectual property, proprietary datasets, or personal information. While poisoning compromises a model during its development phase and inversion exploits it after deployment, both attacks share the core trait of leveraging weaknesses in the machine learning pipeline. If left unaddressed, these vulnerabilities can lead to severe breaches of privacy, trust, and security. Mitigating such threats requires robust data validation, strict access controls, continuous monitoring, and privacy-preserving model design. Data poisoning begins with attackers identifying vulnerabilities in the machine learning training pipeline, such as unsecured data sources, inadequate validation procedures, or weak access controls. Once a weakness is found, they craft and inject malicious samples into the training dataset, often leveraging supply chain weaknesses to ensure the tampered data is accepted without suspicion. These poisoned inputs are designed to subtly influence the model's learning process, embedding hidden behaviors or misclassification triggers, while keeping the model's performance on normal data seemingly unaffected. As a result, the compromised model operates as expected under typical conditions but produces incorrect or malicious outputs when specific triggers are encountered. This stealthy nature makes detection extremely challenging, allowing the attack to persist undetected and posing significant security, safety, and trust risks to AI-driven systems across critical applications. Model inversion attacks involve systematically probing a model's decision boundaries by sending carefully crafted queries and analyzing the resulting output probabilities or confidence scores. By studying how the model responds, attackers can infer gradient directions in the feature space, guiding an iterative optimization process to reconstruct sensitive elements of the training data. This process can gradually reveal private information, such as personal identifiers or proprietary patterns, even without direct access to the original dataset. A notable real-world example occurred in 2019 when researchers successfully extracted facial images from a facial recognition model by exploiting its output responses. This demonstrated that model inversion is not merely a theoretical threat but a practical and dangerous technique capable of compromising privacy, intellectual property, and security, underscoring the need for strict output control, privacy-preserving training, and robust access policies. Detecting data poisoning requires continuous monitoring of model performance for unexpected drops in accuracy, unusual class distributions, or anomalous training patterns that may indicate corrupted inputs. Statistical analysis, data provenance tracking, and anomaly detection tools can help identify suspicious samples before they impact the model. Mitigation strategies include applying differential privacy to limit the influence of individual data points, using output randomization to reduce the information leaked through predictions, and validating data sources to prevent malicious injections. When conducting ethical penetration tests, practitioners should operate within clearly defined boundaries, using only synthetic or anonymized datasets to avoid compromising real user information. Additionally, they should monitor for excessive or abnormal query patterns when simulating model inversion, ensuring that testing remains compliant with privacy laws and organizational policies while still uncovering vulnerabilities effectively. Balancing technical expertise with ethical responsibility is essential in AI security testing. Practitioners must meticulously document all methodologies, tools, configurations, and findings to maintain transparency, facilitate reproducibility, and support informed decision making. Before engaging in any testing, especially on production systems, it is critical to obtain explicit documented permission from the system owner to ensure legal compliance and protect against unauthorized activity. AI security should not exist in isolation, but be integrated into the organization's broader risk management framework, aligning with policies for data protection, operational resilience, and incident response. This holistic approach ensures vulnerabilities are addressed in the context of overall business objectives, regulatory requirements, and ethical standards. By embedding AI security into enterprise-wide risk assessments, organizations can achieve comprehensive protection while upholding trust, legality, and professional integrity.